Hello, welcome to my talk on why we cannot use the Lagrangian approach in fluid dynamics. In this talk, I will first give the detailed differences between the Lagrangian and Eulerian representations for fluid motions. And then I will show the dynamic equations in these two approaches. We will look at the reasons why we do not use Lagrangian approach for fluid motions, and the derivation of the Lagrangian equations for inviscid flows, and the continuity equation in the Lagrangian approach. To describe the Lagrangian representation, we use the example of a steady flow Partial airfoil given as this. In the Lagrangian approach, we need to divide the fluid into many small fluid elements, say n fluid elements, at the initial time t0 equaling to 0. See this fluid element or part of the fluid domain. And the fluid particle can be identified using their initial coordinates. Here A, B, C as the coordinates along x-axis, y-axis, and z-axis. That is x, y, and z at t0. And following the reference, the initial coordinates A, B, C would be the independent coordinates or the variables. And this can be very similar to the coordinates x, y, and z in the Eulerian approach. So in the coordinate OX, Y, Z, this would be same coordinate used in the Eulerian method. The Lagrangian method would chase all the fluid elements in time, see the case element pk at time t1, t2, t3, t4, t5 on the fluid path line or the trajectory see here. And in Lagrangian approach, for a fluid element, its dynamics is very similar to that of a solid, given as this from the Newton's second law of motion. The acceleration along the x-axis times m would be the force component on x-axis acting on the fluid particle, and so on. Here m is the mass of the fluid particle, and capital Fx, capital Fy, and capital Fz are the components of the force acting on the fluid particle. This should include the body force and the surface force based on Euler. Here the important notice would be the coordinate in the Lagrangian approach. X, Y, Z would be the quantities to be solved in the dynamics. Therefore, they are not variables used for represent some quantities. And obviously, the coordinates x, y, and z would be the functions of the initial coordinates a, b, c, and time. So, x, y, z would be the functions of a, b, c, and the time t. For Eulerian representation, we divide the fluid domain into many small elements, say n elements, and all the elements would be fixed in the space, see this element, and all this element would be fixed in the space. For example, the case element. Each element would be identified by its coordinates x, y, and z, and these coordinates would be the independent variables in the Eulerian approach. In the coordinate or x, y, z. This is the same coordinate as that in the Lagrangian approach. Both approaches use the same coordinates fixed in the space. However, the Euler approach studied the fluid behavior in the fluid element. For instance, how does the fluid perform, or how does the fluid pass the element. For each element, since the element is fixed, so its volume delta V is a constant. The dynamics of the fluid in the element would be given by the Euler or Navier-Stokes equation. So the dynamic equation would be given as this. Here, rho delta V is the mass of the fluid in the element. And capital Fx, capital Fy, and capital Fz are the component of force acting on the fluid particle. This would include the body force and the surface force. But in the Eulerian approach, the acceleration is given as the substantial acceleration. Here, we use capital Du or capital Dt as the substantial acceleration along x-axis, and so on. Therefore, the solutions of the Eulerian method are the fluid states in the fluid element. For instance, the velocity would be the function of x, y, z, and t, and the pressure would be the function x, y, z, and t, and so on. That means all these quantities are the functions of the coordinates x, y, z. These are the variables, not the solutions as we have seen in the Lagrangian method, as well as the time if the flow is unsteady. In the Lagrangian representation, the accelerations of the fluid particle would be simple, which are given as the second-order partial differentiation of the position with regard to t. So Ax is given as the second-order partial differentiation of x with regard to t, and y is the second-order partial differentiation of y with regard to t, and the same for z. While in Eulerian representation, the acceleration is given as the substantial acceleration. So x, y, and z would be given as this. Obviously, in the Eulerian representation, the fluid acceleration is much more complicated than the acceleration in the Lagrangian representation. So we can see here in the Lagrangian representation, the acceleration is linear as the second-order partial differentiation with regard to time. And following none in this book, x, y, and z would be the function of other parameters, say the initial position or their identity coordinates a, b, c. And in the Eulerian representation, the acceleration is nonlinear in expression. The part in the box is the nonlinear convective acceleration. For inviscid flows, the moment equation in Eulerian approach are the moment equation in Euler equation given as this. And in the Lagrangian approach, the corresponding moment equation would be given as this. So we can see the force, and especially the surface force due to the pressure, are same. And the only difference between the Eulerian approach and the Lagrangian approach is the expressions of the accelerations. So in Eulerian approach, the substantial acceleration given in this complicated formula, while in the Lagrangian approach, the accelerations are much more simple. However, in the Eulerian approach, the partial differentiation of p with regard to x, with regard to y, and with regard to z can be directly calculated, since in the Eulerian approach, x, y, and z are the variables, while in the Lagrangian approach, x, y, and z are the solutions. They are not the variables. Therefore, the partial differentiations of p with regard to x, with regard to y, and with regard to z must be eliminated or replaced in the dynamic equation. And this is the topic we are going to talk about in the next few slides. Look at the question, why in fluid dynamics the Lagrangian method cannot be used, especially in the 3D viscous flow. The answer for this question would be, in Lagrangian approach, the main difficulties are the surface force calculation due to the pressure and due to the viscous stress, because of the first order or the second order differentiations with regard to x, y, and z. However, in the Lagrangian approach, x, y, and z are the quantities to be solved. Thus, they are unknowns for the dynamic equation. Therefore, the differentiations with regard to x, y, and z in the Lagrangian approach must be replaced or eliminated in the dynamic equation. That is, we need to find ways to replace this expression, if it is possible. For the inviscid flow, the moment equations are given as this in Lagrangian approach, and this part are the acceleration of the fluid particles, and this is the body force per unit mass. Because of the coordinate z pointing up vertically, so the body force is minus g here, and this are the surface force per unit mass due to the pressure. In here, we must say, although in Lagrangian method, the differentiation to x, y, and z are quite strange because x, y, and z are unknowns. But the calculations of the surface force due to the pressure are correct, since this would be same as in the Eulerian approach, and all these surface forces are derived only regarding to the particle position x, y, and z. But the problem in the Lagrangian approach is x, y, and z are unknowns. We need to solve them in the dynamic equation. Therefore, in building the dynamic equation, we must find the replacement for the expressions. The partial differentiation of pressure with regard to x, with regard to y, and with regard to z in the dynamic equation. Following Lam in the book, the coordinates of the fluid particle motion x, y, and z can be solved from the dynamic equation based on the initial coordinates a, b, c. Therefore, we can assume x, y, and z would be the functions of the initial coordinates and the time. So, it would be given as the position of the particle given as the coordinates x, y, and z. And all these coordinates would be the functions of the initial coordinates a, b, c, as well as the time t. Here, and following the book, we can take the initial coordinates a, b, c as the independent variables This is very similar to the coordinates in the Eulerian representation. Now we can calculate the pressure gradient using the independent coordinates A, B, and C. So, using the chain rule of the differentiation, we can obtain the partial differentiation of P with regard to A. It would be given as the expression as this, the chain rule of differentiation. So here we can see the partial differentiation of P with regard to X, P with regard to Y, and P with regard to Z here. And similarly, we can calculate the partial differentiation of P with regard to B and P with regard to C. And we also see the partial differentiation of P with regard to X, P with regard to Y, and P with regard to Z. So if we write the expression as the equation, so we have the equation as this. This matrix is called Jacobian matrix or determinant, and it also can be written as in this expression. So from this mathematical equation, we can solve the partial differentiations of P with regard to X, with regard to Y, and with regard to Z given as this. So here it's the inverse of the Jacobian determinant. Mathematically, these expressions can be used for getting the differentiations of P with regard to X, with regard to Y, and with regard to Z. But this expression is a complicated mathematical expression with the inverse of Jacobian matrix. However, for the inviscid flows, we may have a simpler method for getting the partial differentiations of P with regard to X, with regard to Y, and with regard to Z. And following the Nahm's book, Hydrodynamics, the moment equation for the fluid particles in Lagrangian representation is expressed as in a more general form. Here, the body force are given as Fx, Fy, and Fz. And this would be same as the equation as this if we take Fx and Fy are 0 and Fz equaling to minus g. Now from this expression, we can easily calculate the partial differentiations of the pressure with regard to X, with regard to Y, and with regard to Z given as this. Now we look at the partial differentiation of the pressure with regard to A. For these terms, we can substitute these expressions into this expression, and we can obtain the equation given as this. So this part is the partial differentiation of the pressure with regard to X, and this part is the partial differentiation of P with regard to Y, and this part is the partial differentiation with regard to Z. So this equation can be further written as this form. And this is the moment equation on x-axis for inviscid flow in Lagrangian representation. And now we can see x, y, and z are the unknowns. And all the partial differentiations with regard to x, y, and z are removed. Principally, this equation can be used for solving the unknowns x, y, and z, as well as the pressure P. Now, similarly, we can obtain the moment equation corresponding to the second and the third moment equation given as this. And from these moment equations in Lagrangian approach, we can see x, y, and z, as well as the pressure P, would be the functions of the initial coordinates of the fluid particle A, B, and C, as well as the time t. Unlike the Eulerian approach, where we can have a case called a steady flow, and in there, the parameter time would disappear. That is, the parameters are all time independent. But in Lagrangian equation, the parameters x, y, z, and p are always time dependent unless the fluid is static. So these are the 3D Lagrangian equations for inviscid flow. And from the book, these equations were derived by Euler, although they are called the Lagrangian equations. Obviously, Euler derived both Euler and Lagrangian equations for fluid motions. Now we can examine the 3D viscous flows in Lagrangian approach. The equation of the 3D viscous flow in Lagrangian approach would be given as this, and the terms on the left-hand side are the accelerations of the fluid particle, and Fx, Fy, and Fz are the body force of the fluid particle. These are the surface force due to the pressure, as we have examined in the previous slide. And we have the surface force because of the fluid viscous stress. And we can see here the fluid viscous force would be the second order differentiations with regard to x, y, and z. Here, the velocity components of the fluid particle u, v, and w are calculated given as this. Now the question whether we can replace the first and the second order differentiations with regard to x, y, and z as we have done for the inviscid flows. The answer for this, according to the reference, it can be only done in 2D cases. You can find the details in the reference. But the Lagrangian equations for 3D viscous flows are remaining an open question. That is, we don't have the Lagrangian equations for 3D viscous flows. In the last slide, the continuity equation in Lagrangian approach is presented. In the Lagrangian approach, the continuity equation is given as this, based on the reference here. Rho here is the fluid density at the coordinates x, y, and z. And rho 0 is the initial density of the fluid at coordinates a, b, and c. And the Jacobian matrix is given as this. We have seen this in the previous slide. If the flow is incompressible, that means rho would be same as rho 0. Therefore, the Jacobian matrix would be equivalent to 1.